Okay, good morning, everybody. I'm going to introduce to you today a process to write electron configurations. You have no idea what that means. Electron configuration, what in the, Mr. Allen, seriously? Electron configuration, that sounds like you made something up. It's actually kind of cool because, and this is the stuff where I go, how do they know that stuff, right? But this is kind of cool because let's say I have a carbon atom. And I want to know, how do the electrons fill? Because we talked about the number of electrons in a Bohr model. Like carbon, in the first energy level, it has 2 electrons. In the second energy level, it has 4, right? So it's got a total of 6. So today we're going to talk about how those electrons fill and in what order. In what order? So if I took a scoop, if I have a carbon's got 6 protons and 6 neutrons, right? If I took a handful scoop of electrons and just threw it at that nucleus, I can tell you how the electrons fill. What? And today, after this block, you'll be able to tell people. Today, by the end of this block, you're going to go, I got this. I got this. Are you ready for that? Okay, so here's how it goes. If I'm filling orbitals and electrons, first of all, I got to understand how the periodic table is broken down. Remember we talked about pattern recognition? This is the ultimate in pattern recognition, understanding how the periodic table is built and understanding how it's arranged so that you know how these electrons fill. Oh, I almost forgot. Remember when we talked about this? We're going to talk about this later. It's later. We're going to talk about the middle. We'll talk about the middle later. Today's later. So we're ready. This is where we're going to talk about the middle. Right? We said at first we're just going to ignore 1, 2, 3, 4, 5, 6, 7, 8. We'll skip the middle. We'll talk about that later. That's today. Okay. So periodic table is broken down into 4 main area groups, and they're called orbitals. This group 1 and 2. Don't write anything on your periodic table until you feel comfortable saying, okay, now I know how I'm going to do this. Okay? But just follow along. Maybe take some notes. But then I want you to eventually write on your periodic table so that you have something comfortable, so you understand how to read your periodic table. Everybody with me? Okay, so this first 2 groups, this is the S orbital. S. All right? And it actually, S, I think, there's some speculation out there. S stands for spherical. The electron arrangement is spherical. Then the group up here, remember we talked about these 2 raised up levels? These 2 raised up ones are kind of together. We call those the main block elements. This is the p orbital. Okay? The middle, talk about that today. I'm excited. This whole middle, the transition metals, this is called the d orbital. I think this is spherical, principal, diffuse, which means sort of ambiguous. And then down here is the F. That's not your grade in chemistry. That is the orbital F. And I don't know if that's frequency. Seriously, I don't know. SPDF, people call them different things, but you can look it up. Okay, so S, P, D, and F. So everybody understand that. There are 4 areas of the periodic table. They just have different letter designations based on how their electrons fill and in their orbitals. We'll talk about orbitals as we discuss this too. Is everybody clear? Okay, and it's like right now you're going, clear, Mr. Allen, you just circled 4 parts of the periodic table and put letters by them. How am I supposed to be clear about that? That's all you need to know right now. This is an S, that's P, this is D, this is F. S, P, D, and F. Okay? So remember what I talked about? If I scooped up a big bunch of electrons and I hurled it at carbon, how do they fill in? Well, this is how we know. We start here. Everything starts here. Everything starts here. Start here. And that is with the first energy level. I'm going to show you how to do electron configurations first, and then we're going to talk about orbital diagrams. I think positive physics mentions orbital diagrams first and then electron configurations, but I really believe it's better to do it in the reverse. So we're going to go 1. Which orbital is it? And how many? 1. So hydrogen would have an electron configuration of 1s1. So this is energy level, orbital, how many electrons? I bet you're sitting next to somebody who knows what the electron configuration for helium is. Helium. Hydrogen is 1s1. Helium is 1. Oh, by the way, helium is kind of a dotted line here. I should probably redraw my p orbital so it does not include helium. P orbital does not include helium. Helium has a dotted line around it because helium is, what do you think, Josh? It's in the S. So I bet you know what helium's electron configuration is. If hydrogen is 1s1, I bet you know helium is, what is it? Bingo. 1s2. Now, in electron configuration reporting, what we're trying to do is go left to right across the periodic table. And once we're there, once we're here, we're going to call it that. So 1s2 gets us all the way across the first row. The first letter is the energy level. The second, or the first number is the energy level. The second one is a letter, and it represents the orbital S, P, D, or F. And then the 2 is the number of electrons in that orbital. Okay, so 1s2 is helium, and that also gets us across the first line. This is where it gets interesting. We're going to take lithium. Lithium is 1s2, right? You guys remember when we did the name game? And we said, you're going to say your name and your Walmart item, and then you're going to say his name and Walmart item, and then your name and Walmart item, and then you're going to say his name and Walmart item, and his name and Walmart item, and then your name and Walmart item. Remember how we did that? Yeah. That's electron configuration. So what we're going to do, on a lithium, we're going to say 1s2, gets me to here, and then we're going to add, somebody help me, 2s1. You guys are geniuses. 2s1. So lithium has how many electrons total? 3. 2 in the first S and 1 in the second S. Because there's 2 across the top. 1s2 gets me across the top row, then 2s1. Any idea what beryllium would be? So beryllium, I'm going to start a row down here. So beryllium would be 1s2, 2s2. Do you see it? Yeah. 1s2 gets me across the top, 2s2 gets me to beryllium. Talk to me. 1s1 only sticks me right here. That's it. 1s2 gets me all the way across. I'm trying to go across left to right, top to bottom until I get to the electron or the element I'm after. All right? So if I'm doing the electron configuration for hydrogen, it's 1s1. Every other thing is going to start with 1s2. Because remember, all we're doing is denoting how the electrons fill in what order on the electron energy levels. So in the first energy level, S orbital, 2 electrons. Boom, 1s2. So the first 2 electrons go in, boom, boom, first energy level, 1s2, right? Second level, lithium would be 2s1, and beryllium would be 1s2, 2s2. Right? How about boron? Boron. See if you're sitting next to somebody who knows what that would be. Yes, Riley, talk to me. You are a genius. 1s2, 2s2, 2p1, second energy level, p orbital, 1 electron. Ah, what are we seeing? Are we starting to see a...
So would boron be like the start of the P?
Yes. So what would carbon be?
1s2, 2s2, 2p2.
What? 1s2, 2s2, 2p2. Carbon has how many electrons? Philip. Total. Total number of electrons for carbon. 6. Watch this. 2, 4, 6. What? So you can add the electrons. It's going to equal the atomic number. Ayrton, you with me? Okay. Nitrogen. One S2, 2s2, 2p3. And then oxygen is 1s2, 2s2, 2p4, etc., etc., etc. I'm going to go all the way to neon. Fluorine, 1s2, 2s2, 2p5, and then neon is 1s2, 2s2, 2p6. Anybody so far so good? Emma, can you do sodium? All right, give it a whirl. Bingo. Sodium. 1s2, 2s2, 2p6, 3s1. Right? Everybody see the pattern? Everybody see the pattern? Is there anybody that still hasn't seen the pattern? Anyone? Philip, hang on right here. So we're on sodium. If I'm on magnesium, I'm going to go 1s2 gets me to there. 2s2 gets me to here. 2p6 gets me to here. 3s2 gets me to here. Right? We're going left to right across the periodic table all the way down to the element we're on. Yeah. They should add up to the number of electrons, yes. So for sodium, they have 2, 4, and 6 is 10, plus 1 is 11, and so, oh what? 11. Okay? So should be, if I'm going to here, I'm going to go top to bottom, left to right, top to bottom until I get here. 1s2, 2s2, 2p6, 3s2, 3p1. Silicone, 1s2, 2s2, 2p6, 3s2, 3p2. Phosphorus, 1s2, 2s2, 2p6, 3s2, 3p3. Follow? Sulfur, 1s2, 2s2, 2p6, 3s2, 3p4. Chlorine, I'm going to write chlorine out. And the reason I'm going to write chlorine out so you're going to see something kind of cool. Chlorine, 1s2, 2s2, 2p6, 3s2, 3p5. All right, we talked a lot about valence electrons before, right? We talked a lot about the Lewis dot diagrams only have the valence electrons around them. And we said chlorine is a halogen, like fluorine and bromine and iodine, halogens, and they have electrons in the outer shell to a total of 7. Very nice. Group 17. So chlorine has 7 electrons in the outermost shell. Count the highest energy level. 3. How many electrons are in that? 7. Highest energy level, outermost shell, valence electrons, total 7. Everybody with me? No?
Can you like go back 2 steps and get back to there? Like the chlorine.
Tell me which part you're confused about, because
Valence electrons?
the number of valence electrons in chlorine is 7 because it's in group 17, right? And we count those because we count 1, 2, 3, 4, 5, 6, 7. So if I go to the electron configuration, I go to the highest energy level, which is 3, and I count the number of electrons in the highest energy level. 2 in the S, 5 in the P, for a total of...
Oh, 3 is the row number.
Yeah.
Oh, okay.
Highest energy level. Outermost shell. Okay. So, yes. What is the what? We're going left to right, top to bottom on the periodic table. So we're going 1s2 gets me to there. Then 2s2, 2p, 1, 2, 3, 4, 5, 6. Then I'm going to go to the next level, and I'm going to go 3s2, 3p6 to argon. Right? So it's left to right, top to bottom on the periodic table. Yes.
That last, I'm confused. I'm still stuck on everything. So, the 1 is the group.
First energy level?
That's the group.
Nope, that's the period.
I mean, period. And
Yep.
the S is the orbit. And then it's the...
How many are there?
Just 1.
1s2. Actually, helium dotted line means it really belongs here from the s orbital. The only reason helium is over there is because its outer shell is full. Full outer shell means it's a noble gas. Well, that first energy level only has 2, so it's a little bit weird. Everything else has 8, 18, 32, etc. But this one only has 2. So helium is here because it's full, but the truth of the matter is helium is still in the s orbital because that's that first 2. Say it again. The number of electrons, correct. So 1s, 2 electrons because there's 2 elements. 2s2, 2p6 gets me to here. And you just think, I'm trying to trace the periodic table left to right, top to bottom, until I get to the element I'm on. So far, so good? Okay, I'm going to give you calcium. Somebody, hey, are there any whiteboards out? You got a whiteboard? Write calcium on the whiteboard. Electron configuration for calcium. You got a whiteboard? Hey, what's happening with the table? Put it down. It should lock. I should hear a snap. Okay, yeah. People aren't that smart. I've seen a kid sit on the edge of the table, and when people do that, they make it loose, and then they sit on the edge of the table, and it goes bang, and then broken elbow. Yeah, not cool. Okay. Everybody good? Calcium, what do you got? We're still almost there. 1s2 gets me to the top. Yep. 2s2 here. 2p6 gets me to here. 3s2 to here. 3p6 gets me to here. 4s2. Genius. Everybody with me? Now, here's where it gets weird. Here's where it gets weird. Let me say that again. Here's where it gets weird. When you get into the fourth energy level, you go 4s2, and then you drop. So this is the third energy level in the d orbital. This is the fourth energy level in the d orbital. This is the fifth energy level in the d orbital, and the sixth energy level in the d orbital. These are notes I would expect you would write on your periodic table to remind you that we have an energy level drop. Energy level drop. So we go 4s2, 3d, 4, 5, 6, 7, 8, 9, 10. 3d10. And then we're working our way across. What happens to the p orbital? Question before that. What's the question? I do. Grab another periodic table. Pass that back for me, please. Thank you. Okay. 4s2, 3d drops down into the third energy level, filling in the d orbital for a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then it jumps back to what? 4 p 6. So somebody write out krypton for me. Whiteboard. Krypton.
So for like if you drew out the atom for an element in the D zone, would there be more atoms or electrons in the 3 line or row?
But not in the outer shell. Because what's the outer shell?
So that would go in with the third shell.
Yeah, they load up 2 in the fourth, and then they start filling back into the third. But the fourth is still the outer shell.
Oh, yeah.
The fourth is still the outer shell. Hey, did everybody catch that? You got? Krypton. Read it off for me. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6. Now, let me say this out loud. There are people that say, always keep your energy levels together. I'm showing you the order in which they fill, not the order in which they are numbered numerically. So 3D is actually, some people would argue, this would be 3s2, 3p6, 3d10, 4s2, 4p6. So I'm going to put a little asterisk, parentheses around that and say all the 3's together, all the 4's together. You got that? I like the way that I delivered because it gives you the indication of how they are filling and in what order. In what order. Does that make sense? So left to right, top to bottom is the order in which they fill. So it's 4s2, 3d10, 4p6. So Geronimo brought up a great question. He said, how is it then that these guys have a different number of electrons? Do they have a different number? I thought the outer shell could only have 8. The second one is by order of energy level. The first one is by order of how they fill. I prefer the top one. Neither of these is right or wrong. They're just different way of looking at the same thing. Got it? So you're going to see diagrams that are by numbers. First energy level, second energy level, third energy level. So I wanted to be able to point that out. I'm telling you 3s2, 3p6, 4s2, 3d10 because that's the order in which they fill. However, be aware that the third energy level has 3s2, 3p6, 3d10, and the fourth energy level has 4s2, 4p6. That's the answer that I'm giving you. Fourth energy level is the valence shell, correct? Right? So we're looking at krypton, Fourth energy level, outer shell electron. How many electrons are in the outer shell in just the fourth energy level? How many? 2 here and 6 here for a total of 8. Makes sense. Krypton's in group 18. How many valence electrons does group 18 have? 8. Genius. See how this works? This is massive pattern recognition. Massive.
If you write it the other way, like the 3D10 and then 4P6, the two last ones would add to 16.
Correct, but one is in the third and the other's in the fourth. So that's why when you write it by last energy level, it's 8. Because 3 is in the lower. So we snuck 10 electrons in under the door. Right? So we filled in the first 2 in the fourth, and then we started filling in the one below it. And we put 10 electrons in there and then went, oh, wait, we better fill in this other one up here. Say it again. It drops after the first 2 fill in the fourth energy level, then it drops electrons into the third energy level, and it fills up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 of them until it goes back to the fourth energy level and fills in 1, 2, 3, 4, 5, 6 of them in the p orbital. Right? Okay. You want to see more weirdness? I don't know if you're ready for that. So the fourth energy, or the fifth energy level kind of does the same thing. 5s2, 4d10, 5p6. So if we wrote xenon, xenon would be, let me write that. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6. Okay? So xenon, fifth energy level, 5s2, 5p6, has the fifth energy level, has 8 electrons in it. Boom. That's the electron configuration for xenon. Now, this is where it gets out of control. Woo! This is why I have you have a paper copy of your periodic table so you can write yourself a little note to remember, hey, weirdness happens here and here and here. So as long as you're looking at your periodic table and going left to right, top to bottom, you can't mess it up. You can't mess it up. These switch down to 3, 4, 5, 6. But before you get here, this goes 6s2. And whoa, we've got a detour. See this detour? It says 57 to 71 is here. 57 to 71 goes here. That means after 6s2, we detour down to 4f. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Yes, 14. And 71 is the beginning of the d orbital. 71 is actually here. I'm going to put a square around 71. 71 takes up this space. Everybody with me? 71 takes up this space. So we're going to go 6s2, 4f, 14, and then 71 is here. So we'd go to 5d, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then 6p6. Yes, I will walk you through that again. When we get to 6 and 7, weirdness happens like nobody's business. So we go 6s2, detour down to 4, and this is 5. 6s2, 4f, 14, 5d10, 6p6. Say it again. That's the energy levels in which they fill their electrons. Okay? So now 7, 7s2, 5f14, 6d10, 7p6. So who wants a whiteboard? Who wants a whiteboard? Jaden wants a whiteboard. Who wants a whiteboard? Have you known me to ever give extra credit? Nope. Oh, you're right. You're right. I gave extra credit 32 years ago because extra credit was always given to those kids who had 97 and they wanted 100. I don't like that. I'd love to give extra credit to a kid who has a 60. That'd be awesome.
Thank you. And an eraser.
Yes.
Oh, thank you. Wait, do you want us to do this?
No, not quite. Are we there yet? Who else wants a dry erase board? You got one? Yep.
Why is 71 and 103 separate from the rest?
They fit in those empty gaps. See the empty gap?
Oh, okay.
This empty gap is 71. And this empty gap is 103. That's how they fill in. Yeah, that's the first D. Yes, this is my physics one. Let me give you that. Okay, let me see if I got some markers. You have a marker, you need an eraser. Correct, F orbital. F orbital. Okay, here it is. On your whiteboard, write the electron configuration for oganesson, which is actually un octium. The OG. That is the OG, the creme de la creme of the electron configurations. Yes. 14. 4F14. We're gonna recap that when we talk about the next thing. Okay, you can pause that. So that is the electron configuration for the original chemistry gangster. Okay, so that's a long mess, yes? Let's see how many of you noticed the other pattern. There's another pattern built in here. Okay, so let me erase a few things. I got kind of electron configurations all over the place here. I'm going to go back to my original clean board so I can show you the periodic table and its awesomeness. Yeah. Okay, so let me get rid of all these. Okay, so that's 3D, 4D, 5D, 6D, and remember 6 and 7 goes D2 or to 4 and 5. F, D, and these are p orbital. Okay, so here's the question. Who noticed, because I know some of you asked questions, how many electrons fit in the s orbital? 2 electrons in the s orbital. Okay? Now, electrons are spinning objects. I'm going to show you a little cool thing. Electrons are spinning objects. And when they spin, the direction of the spin can be done by what's called the right-hand rule. The right-hand rule is actually for a magnetism, but it actually works for electron spin too. So if an electron spin, look at your right hand, is spinning in the direction of your fingers, the direction of the spin is up. Your fingers on your right hand are pointing, so if I look down on it, it's spinning counterclockwise. That's considered an up electron. If you look at your right hand and it spins the opposite direction, what direction is your thumb? Down. So in a pair of ps orbitals, we're going to have a one up, one down electron. One up, one down. Yes. Can't have two up spinning electrons because that would be counterproductive. Now, how many of you noticed how many electrons are in the p orbital? P orbital can have a total of 6. Now, you guys remember when we did Lewis dot diagrams and I said, hey, Josh, don't tune out on me on this one. Remember when I said Lewis dot diagrams, you had to go one on each of the 4 sides and then you can start pairing. And I said, I'm kind of setting you up for something later. It's later. Okay, so we're going to go one up, one up, one up, one up. You have to have an up in each one before you can pair them. How many electrons can the p orbital have? 1, 2, 3, 4, 5, 6. That's 3 pairs of electrons. 3 pairs. 1 pair, 2 pair, 3 pair. Okay? As they fill, remember the whole objective of this was to tell you which electrons fill and in what order. Okay? So if I'm going to fill the p orbital, I can fill it with 1, 2, 3, 4, 5, 6 electrons total, 3 pairs. Because electrons are always in pairs. You ever notice that? When you see the Bohr model, they had 2, 2, 2, 2. They had them in pairs. There's a reason for that because electrons tend to kind of cluster with an up electron and a down electron. Now, let me back up 100 steps and say nobody's ever seen an electron, so we're just speculating based on energy. Okay, so on the p orbital, if I can hold 6 electrons, that's 3 pairs, I'm going to put one up, one up, one up in each of the subshell orbitals because it can hold 6, 2, 2, and 2. I'm going to go one up, one up, one up first, and then one down, one down, one down. Okay, that's the order in which they fill. So, if I'm going to write the electron configuration and spin diagram for nitrogen, nitrogen has what? Go ahead, do that quick. No, it's okay. 100% okay, appreciate it. Okay, so nitrogen has an electron configuration of nitrogen 1s2, 2s2, 2p3. Right? So nitrogen, 1s2 gets me across the top, 2s2, 2p3. Now, if I'm going to draw the spin diagram for nitrogen, it's going to be 1s because it's the lowest energy level. This is for nitrogen. 1s2, 1 up, 1 down. 2s is a little bit higher. 2, 1 up, 1 down, right? 1s2, 2s2. And then 2p3. Well, 3 subshells, each with 1 up. That's the spin diagram for nitrogen. So the spin diagram for oxygen would look just like that, except the first energy, or the first subshell of the P would have an up and a down. Never going to be an empty with an up down. It's always going to be up, up, up.
And then you go to the next energy level. Or it's not energy level.
Come back to the subshell.
Yeah.
So like oxygen, for example, would be up, 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 and then this one would have 2.
Oh. Okay.
So that would be 4. And 5 would be up, 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 down, down. And then up, 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 down, down, down would be the last one. Yes,
Can you turn the thing back on?
I will. Yes.
Yeah, like I said, I'm still like really far behind on actually. But so like, or actually, I can. Oh, okay. So after you go from like magnesium, you move down to whatever that is.
Magnesium.
Then
Left to right. Left to right. Straight across the periodic table. Top to bottom. Left to right. Top to bottom.
so why does that one say three?
Why does what one what?
Because that one also says three. So would it be after you get the argon, you move to that one? Or?
Correct. After argon, you go 4s2, then drop down to 3d10, and then jump back up to 4p6. So the middle, actually by energy level, is shifted down. The middle, if it were written correctly, like if it were 3 straight across, this would be shifted up. Why is it not? See if you can come up with a reason why it's not shifted up. I'll get right back to that. So hang on one second. I'm gonna be on that, but I want to make sure and say, do you know why scandium is not here? Because the number of protons. This has 11 protons. This has 12. This has 13. This has 11 protons. This has 12. This has 21. So if we move these up by energy level, it'd go 11, 12, 21, 22, 23, 24. They don't want to do that. So they shifted it down and said, let's make it match by number of protons. Let's not make it match by energy level.
So does that mean that like when you go, you have to like when you're going across, you have to go by the number of protons?
That's why they're listed here next to this instead of up here, because of the number of protons. And so that's why I said, we're not going to talk about the middle at first. We're just going to ignore that, and later we'll talk about it. Today's later. And so we're saying, hey, it's a weird thing happens in the middle. It's a weird thing. So what happens, hold on. What happens is the fourth energy level actually starts filling electrons. Electron 1, electron 2. Then the next electron that comes in goes to the third. And the next one goes to the third. 10 electrons do that. And then it goes, oh, no more room there, back up to 4. So it goes 4s2, 3d10, 4p6. And this is why I talked about the main block is the one, because that's always the outer shell. S and P always represent the outer shell. What's the maximum number of electrons in the outer shell? 8. As per the Lewis dot diagram, there can only be 8. Because the outer shell is always S and P. I almost slipped and said that a few times. So you guys were like, you would have been like, S and P, what is he talking about? Okay? So let's do a spin diagram for aluminum. Okay? So if I'm going to write the electron configuration for aluminum, where do I? Let's do it right here. Aluminum. You know how to write the electron? What is it? Just trace the periodic table and read it out. 1s2? 2s2? 2p6? 3s2? 3p1. Very good. So that's my electron configuration, 1s2, 2s2, 2p6, 3s2, 3p1. If I were to draw the spin diagram for that, it would be 1s2. 1s would have 2 electrons, up, down. 2s would be a little higher, up, down. 2p would have room for 6, and it would be up, 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 then down, 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 And then 3s2, up, down. And then 3p would have room for 6, and it would have 1. So if you go to positive physics, they start out with the spin diagrams. That's like one of the first things they show you. And I was like, ooh, I would prefer to show you the pattern first, and then we can translate that to spin diagrams. Okay? All right. Questions? Yes. Spin diagrams are the up-downs. Yes.
Is there ever a scenario where both arrows go up?
No, never. So that's one you can eliminate on your positive physics homework. Never going to be pairs of up or never pairs of down. Always going to be this. Questions?